Okay, thanks. All right, so today what we're going to do is this is going to be a very specific lecture, all right? And what I was talking to a couple of students before class about this, but it's really important that all of you understand that I am not going to provide you formulas for these numerical methods. I'm providing you the overview of the method itself. If you have really detailed implementation issues, those things have to be worked out yourself. You've got to figure out, how you want to actually implement the equations. That's not really within the scope of what it is that we do here. I'm providing you the structure and then giving you an understanding of what's going on, and then you have to solve the problems yourself. That being said, the one thing that you all have to be a little bit resourceful about is that these optimization problems have to be solved ultimately with some sort of NLP solver. There are lots of NLP solvers out there. The easiest one to get your hands on is the one that comes with MATLAB. The optimization toolbox is fmin-con. It's not a great NLP solver, but it's okay. The problem is that, well, not the problem, but the issue is you have to learn how to use it. I can't teach you how to use it in this class. You have to just open up MATLAB, and you have to play around with it, and you have to learn how to use it. And if you have questions about it, you can always come and ask me, but I'm not an expert in fmin-con any more than you are. I didn't write it, right? So I'm going to do the exact same thing you're going to do, which is I'm going to open it up, and I'm going to start typing the help and try to understand what it is that's in there, and then figure out how to do this, right? So I'm not fundamentally going to go through any different procedure than any of you will. And this is not a course in learning software tools that you can actually use to solve problems. This is a basic course in mathematical methods for optimal control. So you have to take some of these other steps yourself. And you should probably do it on simple problems. So that's what I'm going to start with today. I'm going to show you the Euler discretization for a simple example. So let's go back to Euler forward. Okay, it doesn't matter which one I use. I can use Euler forward or Euler backward. Either one's going to wind up giving me almost the exact same structure. But if you remember, the scheme looks like this. xk plus 1 equals xk plus hk times f of tk xk. Now, the issue is that we have this grid of points that we're going to discretize at. Let's call this T0. Let's call this Tf. And we're going to discretize at T1, T2, T3, all the way out to, say, Tk minus 1, and then Tf is going to equal Tk. So the collocation, when you write the collocation equations, so in collocation form, if you want to write it that way. See, the way I've written it over there is time marching form, right? I get the k plus first value by applying everything here. But if you write it in collocation form, you've got xk plus 1 minus xk minus hk times f of tk xk is equal to 0. And we do this for k going from 0 up to capital K, all right? So I'm starting here, right? So if you look at those equations, you could see you have to look. Now you have to say, all right, I'm gonna write this as a system of algebraic equations. So you say let, and this is what I did the other day. You say let y equal. So what are the values of x that I'm solving for? I've got x0, x1, x2, all the way up to, let's make this a little smaller, x capital K, right? Because when this is equal, let's make sure that it's capital K. Okay, this may be k plus 1. This is k plus 1. Because, just make sure, this is k minus 1. So then do k here, okay? So if you look at this, you see that the equations have this particular form. And so what I've got is I've got a system. Let's call this system of equations. I've got some g of y is equal to this whole system of equations, which is x1 minus x0 minus h0 times f0, all the way. And then you got x2 minus x1 minus h1 times f1, all the way up to xk minus xk minus 1 minus hk minus 1 times fk minus 1. So that's my system. All right? Now, that's a system of algebraic equations. I can solve that system of algebraic equations. This has nothing to do with optimization yet, okay? So that system is going to be set equal to 0. Now, of course, if I don't have any value in here, now remember, I'm solving a differential equation, right, by some numerical approximation. So I'm approximating the solution. If I don't have a value that's fixed somewhere, this means nothing, right? Because all it's saying is find me a point that satisfies the system of equations, but it's not going to give me the solution to the differential equation because I haven't specified what one of the values is. And remember that in the original differential equation, so in the ODE was stated as x dot equals f of t and x, and I gave you an initial condition, x at t0 equals x0. So this initial condition right here is equivalent to saying x0, well, this is bad notation, but okay, let's call this something else. Let's call this a, okay? So x0 is equal to a, right? So that value is a constant in this, right? Because it's a known value, right? So I can either solve the system the way it is, or what I can do is I can add an equation. So I can either substitute a into this equation here. That's the first thing I can do. Or I can add another equation to this system, which is that you can add the equation. This seems like a dumb equation to add, but this is often how people do this. x0 minus a equals 0. So then the system, the total system, is as follows. It's going to be x1 minus x0 minus h0 f0 all the way up to xk minus xk minus 1 minus hk minus 1 fk minus 1. And then there's an additional equation in here, which is x0 minus a, and then this whole system is now equal to 0. Now you can see that, well, this is a trivial equation to solve, right? But I could either have substituted it in there or not added the equation. But I haven't done anything, right? Because this variable this is treated, x0 is treated as a variable in this problem. If I say x0 minus a equals 0, it's just the same thing as saying x0 equals a and eliminating that variable in the first place. So it's not even in the problem, right? So that gives me a way of doing this. Now, this Euler method has this really interesting feature that, let's suppose I call this whole thing, let's suppose I call it, I called that G, didn't I? Well, let's call it G. Still call it G. It's a new G. All right? Is that you're gonna do this, so we need to solve G of y equals 0, right? It's a root finding problem. So if you want to solve a root finding problem, one way to do this is by Newton's method, right? So Newton's method would do this, is that we pick a point, we say G, we do the iteration by G of y plus delta y equals 0, and then we do a Taylor series expansion, and we get G of y plus the partial of G with respect to y times delta y is approximately 0, right? And what we get out of this is we get that delta y is equal to minus the partial of G with respect to y inverse times G of y. So if we write that in an iteration, we can get y of j plus 1 is equal to yj, and then minus the partial of G with respect to y inverse times delta y j. All right, so this gives us a way to be able to solve this iteratively until we get a solution to this problem. Right? That makes sense? Now, the problem is there's no optimization in this, right? So when we actually do optimization, or when we're solving an optimal control problem, we need to add to this optimization. So now let's look at a specific example where we would employ Euler forward and look at the NLP that comes out of this. Because remember, I told you that all of these methods ultimately lead to a nonlinear programming problem, right? So let's look at an example in optimal control. An example using Euler forward to solve an optimal control problem. And I'm going to make this a fairly straightforward problem, so that we're not to solve an optimal control problem. So the focus here is not on the equations in the optimal control problem. We're not going to get some really complicated, multi-rev low thrust orbit transfer that takes you to Mars or something like that. Okay, this is going to be a very simple problem, all right? Because nothing makes any sense unless you do it for a simple problem. So here's the problem. All right, it's a problem. It's actually a really interesting problem, but it's a problem that looks like this. The cost function is a quadratic cost, 1/2 the integral from 0 to tf of x squared plus u squared dt. I don't want to do a linear problem, so I picked this problem on purpose. Okay, x dot is equal to minus x cubed plus u. And I have the following boundary conditions. X at 0 is equal to x0. No, I'll call this A. X at tf is equal to b. And tf is fixed. So this is a simple optimal control problem. But I want to discretize it now using that Euler method so that all of you can see what this looks like. All right, so how do we do this? All right, well, remember, I purposely picked a problem that had a Lagrange cost, because you not only need to discretize the differential equations, you need to discretize the cost function too, right? You can't do this without discretizing the cost function. So we're going to set up this system of collocation equations together with a cost function that's going to be an approximation of that cost functional by Euler forward. Now, for simplicity in this problem, let hk equal h equal a fixed step size. Okay? So we're not going to break this up. This means that the problem, we're going to have a uniformly spaced time interval. Time interval. Okay? So T0 to TF is going to look like this. We've got T0, we've got TF. Whatever these are, these divisions are going to be exactly the same width. As close as I can draw them on the page. Okay? So these are all going to be width h. Okay? Okay. Now, let's go about doing this, all right? So what do we have to discretize in this problem? Let's look and see what the variables are. Well, we have a state, so we have to discretize the state, control, and time. Okay? So if I'm going to discretize the state, right, I've got the state is going to be discretized. Well, let's start with time. Time is the first easy one. Time, right, is going to be discretized as follows. I'm going to have T0 plus H, T0 plus 2H, all the way up to what? Well, the final value is going to be TF, right? So whatever number of segments, let's say I have k intervals here. So what's the last? What's the? Well, before I do this, let's actually do the interval width. Okay. So time. Let's do this again. So I know h is going to equal what? It's going to equal tf minus t0 over k. Does that split me up into k evenly spaced intervals, or am I off by one? Am I off by one here? If I do this, right? If I do this k times, right? Let's do it, right? So so that you can actually see that there's a lot of things that you have to keep track of when you do this, all right? So I've got T0, I've got T0 plus H, T0 plus 2H, all the way up to TF. But the question is, when I add h to this thing, when I get to the end over here, right? If I say t0 plus k times tf minus t0 over k, what do I get? What's that? What do I get? I get t0 plus tf minus t0, which gives me tf, right? So there are going to be k of these. Is that k intervals or is that k plus 1 intervals? I'm going from 0 up to k. How many do I have? You have k plus 1 intervals, right? Well, you got k plus 1 points, right? You got k intervals, you've got k plus 1 points. This is k intervals, but it consists of k plus 1 points. These points, by the way, these are what are typically called in collocation, these points ti, for I going from 0 up to k, are called mesh points. Because what I've done is I've divided this thing into a mesh, right? That's my time mesh, right? So I have a mesh there. Now, what happens is I've got this system of equations that arises from the Euler discretization. So I need to do something else here. So time is discretized this way. Now the state. What about the state? Let's look at that. Where am I going to discretize the state? Well, I've got x0, I've got x1, all the way up to xk, right? So I got k plus 1 of those. What about the control? Okay, state's going to be discretized at all those points. Where's the control going to be discretized? I'm using Euler forward. What do I know about Euler forward? Euler forward propagates the system from the current point to the next point using the value of the right-hand side of the dynamics at the current point, right? It doesn't use the value at the next point, right? There's no it's an explicit method. It doesn't use the value at the next point. So where is the control going to be discretized? Well, I'm going to discretize it at the first point, at the second point, and where's the last point that I'm going to discretize the control? What's this? Is this UK? It's k minus 1, right? Because I can't discretize at the final point because my last step takes me from k minus 1 to k, and when I get to k, I stop, right? So you see how many variables I have here. I have k plus 1 values of the state, but and how many values of the control do I have? I have k values of the control, right? So I have one less value of the control, right? So I've got time, state, and control. And since tf is fixed in this problem, I don't need to worry about it. It's not a variable in this problem, okay? So the dynamics from Euler forward, what we get is this, is that the dynamics look like this. xk plus 1 is going to equal xk plus h times what? Times minus xk cubed plus uk. And this goes from k equals 0 up to k minus 1. Right? Does that make sense? Right? I start at 0 and I go all the way up to k minus 1, and that gives me, and when I get to k minus 1, what have I got? I get x at capital K, which is my last point, right? So this gives me, so if I write this in collocation form, I've got xk plus 1 minus xk minus h times, I'm writing this out explicitly, so I don't want to rearrange the algebra here. So equals 0 for k going from 0 up to k minus 1. So these are my collocation equations for that particular example. Now, the next thing I have to do is I have to discretize the cost. I'm not doing this in any particular order. So now we have to approximate the cost. Cost functional. So I know that j is equal to 1/2 the integral from 0 to tf of x squared plus u squared dt. Now, the method I use to discretize that cost has to be the same method I use to discretize the dynamics, right? Because the dynamics are being integrated. This is an integrator. It's a numerical integration scheme, right? So this is an integration scheme. So whatever that integration scheme is that I'm using to propagate the dynamics, I must use the same thing to approximate this. When you do this now, this gets into this concept of what's called quadrature. We're actually approximating the integral by what's called quadrature. You've done this before. You've done this in calculus, where I'm just going to give you a really simple thing. When you were doing calculus, you learn these dumb rules where you have a curve, right? And you say, okay, I want to approximate the integral of the curve. So what you do is you break it into a bunch of segments, just like I did over there. And you say, I want to approximate the area under this curve by using these points as in the interval. And what were the dumb ways that you learned? There are lots of dumb ways, right? You learned rectangular rule, where you approximate everything with a rectangle, where it's held constant at, say, the value at the end of the interval. That's the equivalent of Euler backward, right? Or I could do rectangular rule, where I approximate with whatever's at the beginning of the interval, right? So I can do it this way. That's Euler forward. That exactly is what's called Euler forward, where you take that and then you sum up all the rectangles, right? And that gives you an approximation of the area under the curve. And if you make the rectangle width small enough, then you get a better approximation than if you make the rectangle widths really, really big, right? Well, that's what we have to do here. So we have to do a rectangular rule approximation. But when I say rectangular, I actually mean Euler forward. So we're going to approximate this with Euler forward. So what we're going to do is we're going to say the integral from 0 to TF of x squared plus u squared dt is going to be approximated by the following summation. It's going to be the sum from k equals 0 up to k minus 1. Let me make sure that's right. K minus 1. Yep. Of xk squared plus uk squared. And now each one of these has a width of h, right? Because I'm using a fixed width on this thing, right? So each one of them is going to be the value of that function at that particular point, multiplied by the width of the interval, right? Because the width of all these intervals is h. So this is going to equal h times the sum from k equals 0 up to k minus 1 of xk squared plus uk squared. So then what happens is, then the cost functional, remember that's a functional, is approximated via the following cost function. It's not a functional anymore. Cost function, which is that we say J is approximated by what I'm going to call JA, which is an approximation to this, which is equal to H times 1/2. So I got H over 2 times the summation from k equals 0 up to k minus 1 of xk squared plus uk squared. So now that's my cost function. And I need to minimize that, right? Because my original statement was to minimize that thing over there. So now I'm going to minimize this. Now, what have I missed? So I have my collocation equations by Euler forward. I have an approximation to the cost functional, which is a cost function, which is obtained again by Euler forward, because I'm using fixed width Euler forward. There's something that's missing. What's missing? I haven't taken it into account yet. Yeah, I haven't taken into account the boundary conditions, right? I have to take into account the boundary conditions, right? So I have to actually be very careful with that. You have to be very careful with the boundary conditions, because you have to map what you mean by x at 0 and what you mean by x at TF to this discrete problem that you've now created, right? So x at 0 corresponds to a variable in this discrete approximation. What does it correspond to? There's a variable in this discrete approximation that it corresponds to. What is it? It's little x0, right? What about x at TF? What does it correspond to? X what? Capital K, right? So those now are going to equal A and B respectively, right? So now what I've got is the boundary conditions. Now, it doesn't look like these are approximations. The boundary conditions are approximated. They're approximations, okay? They're not the true boundary conditions, because the true boundary conditions are for the continuous problem. Are approximated, sorry, as x0 minus a equals 0 and xk minus b equals 0. So now let's look and see here. Okay, let's look at, now we have to take stock of the whole thing and see what the variables are in this discrete approximation that we've created. So what are the variables? What are the variables in the discrete approximation? This is what you have to do when you solve these problems. I do the exact same thing. I'm going to sit there and bookkeep all this stuff. Yes?
I'm kind of confused about something.
Yeah.
Why did we sum from 0 to k minus 1?
Why do we sum here from 0 to k minus 1? Because you don't have the value of u at k. Right? Because k is approximated at the beginning of every single interval, right? I don't have k here. I mean, I don't have u here. The last value of u I have is that value right there. Because I'm using Euler forward, right? Euler forward is the propagation that starts at the current point and goes forward one step, right? So when I'm at the second to last point, I have the value of u there. But when I propagate to this point, I have the state at the end point, right? But I don't have the control at that end point because I'm done when I get there, right? So Euler forward says stop when you get to the last point. The last point in this case is at TF, which corresponds to the value, the segment where you get to k, right? You're going from 0 to k. So you got k plus 1 values of time. So you went to k plus first value of time. You have the state. You stop there. That's the last equation. But there's no value of the control at that point, right? So that's why that sum goes from 0 to k minus 1. See, that's, again, something you got to keep really, you got to be, if we were doing Euler backward, then the summation would be different. Now the sum would be from 1 to k, right? Because the control would be approximated at the end of each interval, not at the beginning of each interval, right? So that's the difference between the two schemes. So the variables in the discrete approximation, that's a good question. So the variables in the discrete approximation are as follows. Let's list them all out, okay? So, and then we'll group them, because we have a nice way of being able to group them. I've got the state at x0, x1, x2, all the way up to x capital K, right? That's one group of variables. I've got the control at u0, u1, u2, all the way up to u k minus 1. Do I have anything else? Are there any other variables? Anything else? TF is fixed in this problem, right? So I've taken it into account by dividing the interval up, right? Right, because I picked h. Remember, I picked h to be TF minus T0 over K. So I've already chosen it to be that particular width. So I have my value of h, right? TF is fixed. T0 is 0. Okay, so those are the variables. Now, what are the constraints? Now I have constraints, right? Because I've created all these constraints. So the constraints are the following. I've got x k plus 1 minus xk minus h times minus xk cubed plus uk equals 0. And that goes, k goes from 0 up to k minus 1. Do I have anything else? Those are the only constraints I have? I got the boundary conditions too, right? I've got x0 equals a, or x0 minus a equals 0, and xk minus b is equal to 0. So let's start counting, okay? Because it's really important to count. This is something that once you get into the optimization part of this, you begin to realize that, okay, this starts to make some sense, all right? It really does make a lot of, optimal control really does make a lot of sense. How many variables do we have? So let's count. So the number of variables. What do we have? We've got 2k plus 1, right? All right? I've got k plus 1 plus k, right? So 2k plus 1. How many constraints do we have? I have k here plus 2. Right, he's right, k plus 2. Do I have more variables than constraints or less variables than constraints? I have more variables than constraints. Okay, should I have more variables than constraints? Or should I have fewer variables than constraints? Or should I have the same number? Why should I have more variables than constraints? Because there's more than one solution, right? If I don't put a cost on this, if I don't say what is it that I'm optimizing, I can say that there are lots of values of the control that will get me from this point to that point via this approximation that will satisfy that system of equations, right? But in optimal control, you're looking for the one control that optimizes some performance index, right? So you have to have a what? You have to have an underdetermined system. If you don't have an underdetermined system, you don't have any degrees of freedom, right? You have to have degrees of freedom in these problems. So you always have to have more variables than you have constraints. So the number of degrees of freedom, because these are all equality constraints in this problem. If they're inequality constraints, this gets more complicated, is 2k plus 1 minus k plus 2, which is equal to k minus 1, right? So I have k minus 1 degrees of freedom, which is exactly the number I should have, right? Because I should have the control, the freedom to be able to choose the control at all these points that I've actually created, but not quite, because I have boundary conditions, right? So the boundary conditions take out degrees of freedom, right? Because those are two additional equations. How many values of the control do I have in this problem? I have k, right? The initial condition, and then I've got the final condition, right? So if I didn't have the final condition, I would have k degrees of freedom, right? But I've specified the final condition too. So I've removed another degree of freedom. So I have k minus 1 degrees of freedom. So I've got more variables than constraints, and I've got degrees of freedom. So now what I've got is these are the constraints, and then here's my cost function. So my cost function is that approximation that I have over there. So now so if we look at this, we see that the cost function, which is JA, is equal to h over 2 times the sum from k equals 0 up to k minus 1 of xk squared plus uk squared, all right? So now you look at that and you say, all right, so what is the problem that I've just created by doing this discretization? So the problem is this. Let's call these the constraints. Okay, we'll call them C. They're the constraints. No, let's not call them C. Let's call them 1. Okay, and we'll call this 2. So the problem is minimize 2 subject to 1, right? So let's minimize that cost function subject to those constraints. So what have I done? I have created, this is a nonlinear programming problem. It's a nonlinear optimization problem. Also called a nonlinear programming problem. Which we abbreviate as NLP. All right? So you see what happens here is I've done this Euler discretization. I've taken out, remember the original problem is an continuous time optimal control problem. It's an infinite dimensional problem. I'm solving for the state and the control as a function of time that optimize a performance index, which is my cost functional, right? Minimizing the cost functional subject to the additional constraints of the boundary conditions, right? I've transcribed it by doing this approximation, or I've done a discrete approximation. I've turned it into a finite dimensional problem, right? There are a finite number of variables in this problem that need to be solved for, right? So that's the key thing, is that I've done this by transforming it into a new problem that hopefully is a good approximation to the original problem, and I want to find a solution to that approximation and see whether or not that approximation is a reasonable representation of the solution of the original problem. How good is the approximation? The approximation is only as good as the manner in which you discretize the dynamics, because whatever method you use to discretize the dynamics, it's going to be governed by whatever the accuracy of that method. If that method's not very accurate, your approximation is not going to be very accurate. If that method is extremely accurate, your approximation is going to be extremely accurate as well. But one thing you can say when you do this with Euler forward is you can see that it's pretty simple, right? I mean, the equations come out very, very simply, right? Now, one thing that is interesting about this is you can program this up on a computer using a bunch of different NLP solvers. And one of the things you find about these is that these problems that come out of collocation, because of the way collocation is done, it's fundamental to collocation of differential equations, is that these problems are what are called sparse. So the NLP is actually sparse. So what I want to do is I want to talk to you a little bit today just about sparsity. Okay, what do I mean by sparse? So let's look at these. Let's look at this as a grid. I'm going to just look at the constraints. When I say sparse, let's examine the constraints. And what I'm going to do is I'm going to draw a little map here. So this map looks like this. This direction are the variables. Well, I'm going to give myself a little more room here. So this direction here, draw this a little lower. Hang on, let me give myself a little more room. I want to make sure I don't run out of room. So this direction, variables. This direction are constraints. Okay. Now, if you look at this, what are the variables? I've got x0, I've got x1, all the way up to x capital K. Then I've got u0, u1, all the way up to u k minus 1. That's my last variable. This one over here, I'm going to label each one of these constraints. I'm going to call them CK. I'm going to call this B1. I'm going to call this B2. All right, these are boundary conditions. Those are the collocation constraints, right? So if I look at the first collocation constraint, which is where k equals 0, I've got, well, actually, you know what? Let's make sure. I'm gonna move this over. I'm not gonna put this right at the edge. Let's make this x0, okay? So I'll start it here instead of starting it right at the edge, because then I'll give myself a little room here. So this is C0, and then C1, and then I keep going all the way up to C k minus 1, and then I've got B1, and I've got B2. So what I'm going to map out here is I'm going to map out what functions depend upon what variables. So let's look at the first constraint when k is equal to 0, C0. What is C0 a function of? I'm going to mark it over here. Is C0 a function of x0? Yes, it is, right? So I've got a point there. Is C0 a function of x1? Yes, it is. But is it a function of any of the other x's? No, it's not. What about the control? Which values of the control is it a function of? It's a function of this value right here, right? What about the next one? What about C1? What's it a function of? What's C1 a function of? x1 and x2, right? Is it a function of anything else? No, it's a function of u1, right? So if you keep creating this band, you'll see that what you get is you get this pattern that each of the values of the constraints is only a function of two values of the state and is only a function of one value of the control. Everything else is 0, right? There's no other functional dependencies in this. So what's the size of this matrix? Remember how many constraints I've got. I've got how many constraints? K plus 2 constraints. So I have K plus 2 constraints. Let's write this out. You have K plus 2 constraints. And I've got how many variables? 2k minus 1 variables, right? So that means that if I take the constraint Jacobian, which is the Jacobian of these, call this the partial of C with respect to y, where that's my full constraint Jacobian. This is a matrix of size k plus 2 by 2k minus 1. But how many non-zeros are in this Jacobian? You can actually count them up. There are 3 non-zeros in each one of these, right? And how many of them do I have? What's that? No, I'm just the C's. Just do the C's. I've got k of them, right? So k times 3. So I've got 3k. So with how many non-zeros? So let's write out the number of non-zeros. Is equal to 3k. That gives me all of the differential equation constraints. What about the b's? What are they functions of? The first one is a function of x0. It's not a function of anything else. The last one is a function of xk. It's not a function of anything else, right? So I just have plus 2 more non-zeros, right? So I have 3k plus 2 non-zeros, but look at the size of the matrix. The matrix is order k squared elements, right? So I've got order k squared elements, but only 3k plus 2 of them are non-zero. So this Jacobian the constraint Jacobian is sparse and becomes increasingly more sparse as k gets large. So if I have a very large value of k, so I'm breaking this up into a lot of tiny little intervals, then the density of that Jacobian goes down as I increase the problem. So as I make the problem bigger, I improve the sparsity, right? So the NLP solvers that have been developed over the last 10 years, 15 years, there's some very, very good ones. And they've been targeting these large, sparse NLPs. And one of the main areas of technology that they actually were targeting was trajectory optimization, because inherently when you solve trajectory optimization problems by collocation, you get large, sparse systems. And in fact, you get this pattern of like this bandedness and these diagonals show up in all these collocation methods, whether it be Runge-Kutta, Euler forward, Euler backward. You use an Adams multi-step method. It doesn't matter what you use. You always get sparsity because each equation is only influenced by adjacent points. It's not influenced by all the points in the interval, right? I mean, all the points, all the variables in the problem. It's only influenced locally by each of the variables that influence that particular equation, which is why you get this particular bandedness, right? So you have this sparse system. So now what we have is we have a sparse NLP. So what I'm going to do next week I don't like doing this in class because it's not a very easy thing to do, but I'm going to set up one of these problems and I'm going to show you what it looks like, and then I'm going to solve it with one of these NLP solvers. I'll solve it with like SNOPT or something. I'll bring it in and I'll just show you the solution. And you could see what happens to the solution is you keep varying this value of k, and then I'll just send you guys all the code so you can look at it. It's really pretty simple. But that way you can actually see like what this is all about. You can see how it actually plays out. Now, one thing that is really important, this is the last thing I want to talk about today, is that typically in these methods, we don't typically discretize the interval t0 to tf. Because imagine that you have a very large time interval where tf gets really, really big, right? That means what you're going to do is you're going to keep extending out this value of tf. And let's suppose that tf was actually free in the problem and it wasn't a fixed value. That means that you don't know the length of this interval ahead of time, right? So you have to figure it out. So what they do is, typically what we do, the interval t0 to tf is mapped to -1 to 1. You can map it 0 to 1, you can map it 0 to 2, or whatever it is. And the way it's done is this, is that if you start with t lying between t0 and tf, and I want to map this to -1 to 1, here's the transformation, right? First of all, if I subtract t0 from this, I get 0 lies between t minus t0, which lies between and has an upper bound of tf minus t0. If I then divide by tf minus t0, I get 0 is less than or equal to t minus t0 over tf minus t0, which is less than or equal to 1, which gives me 0 is less than or equal to 2 times t minus t0 over tf minus t0, which is less than or equal to 2, which says that negative 1 is less than or equal to 2 times t minus t0 over tf minus t0, which is less than or equal to 1. And we call this thing minus 1. It's less than or equal to 1. And we call this thing, our new variable, we call it tau, or you can call it s, whatever you want to call it. So then what you do is you map everything to the interval negative 1 to 1. And if you look here, you'll see that there's a really easy transformation that comes out of this whole thing, which is that if I'm mapping from t to tau, then the dynamics, I've got dx dt is equal to f of t and x, but dx dt is going to equal dx d tau times d tau dt, which is equal to f of t and x. I haven't done the transformation completely yet, right? Dx d tau, what's d tau dt? Well, if you look at this, if I take d tau dt, what do I get? I get 2 over tf minus t0 times dx d tau is equal to f of t and x. So when I rewrite this, I can write this as dx d tau is equal to tf minus t0 over 2. And then I say f of tau x, and now this becomes a function of t0 and tf, right? Because t is a function of t0 and tf. Because if I write t in terms of tau, if I solve this back for tau, I get something that's a function of t0 and tf. So they become parameters. Now you can actually replace it, and you can do all your discretization on tau if these two values, tf and t0, happen to be parameters in your problem, meaning tf is free or t0 is free. You can add them in as additional variables into your discrete approximation. They just become two additional variables in your discrete approximation. You're always working on the interval negative 1 to 1. So your mesh is always being discretized on negative 1 to 1. Okay? So that is a starting point for collocation methods. By the way, yes, go ahead.
What happens if you have an infinite horizon?
Infinite horizon problem. You would ask that question, wouldn't you? Yeah, that's a really, really good question. The way that's done is, well, it has to be done very, very carefully. But if you want me to talk about infinite horizon problems, we've actually done some research on actually mapping finite infinite horizon problems to finite domains and stuff. It's not a simple answer. It requires a little bit more depth. But I can talk to you about it as later on. We actually have a paper that was published in Automatica last year where we actually talked about exactly this topic. But it's complicated. Complicated in the sense that it's not a 2-minute answer. It requires a little bit more discussion. But I can do a lecture on it, a part of a lecture on it, if you want to see some of that stuff. Okay. The main thing I wanted to get across here, I've never done this lecture before, by the way. This is the very first time I've actually gone through. I thought about this a couple days ago because what I realized was we're operating so much in the abstract with these equations, and you can't see like what any of this stuff really looks like. So what I decided to do was I decided to give you a concrete example so you could see like how all the structure, how it all lays out. Now, of course, if your problem's more complicated, if you have multiple differential equations, you got a more complicated cost function, you're going to have to adapt this to that particular scenario. So you get a number of variables is going to grow and number of constraints is going to grow. But the idea is the same. We still get these for each state. You have a set of discrete approximations that come out of the discretization, and you do that for every single state in your problem. And now you get one for each differential equation. You get a discretization. So I wanted to map this out so you could all see this, because this is really, really useful. This is where you take the power of nonlinear optimization comes into play. I haven't talked to you yet about some of the details of nonlinear optimization because I wanted to go through this first, because now you have a context for why are we going to learn anything about nonlinear optimization in this class. So we're going to do that later, and now you have a reason as to why we're going to do this, rather than it just being something really abstract and generic. Okay? So we're going to stop here. There's no class on Friday because I'm actually out of town, so we'll do a makeup lecture next week. All right? We're going to have 4 lectures next week. I'll schedule the makeup lecture with Chuck Potter. We'll figure out a time to do it. Okay? So it's going to be the 3 regular lectures next week plus a makeup lecture. Okay?